Two concentric coils. A circular coil with N1 equals 5000 turns is made of a conducting material with resistance 0.01 ohms per meter and radius A is equal to 40 centimeters. So that's this coil here. N1 turns and radius is equal to A. A second coil with radius B is equal to 4 centimeters, 10 times less than that of A, made of the same wire, with N2 equals 1000 turns. It's made of the same wire, so it has the same resistance per meter. N2 equals 1000 turns, is concentric with the first coil and parallel to it. That's this one. The capacitor has a charge of 100 microcoulombs on its upper plate and the switch S is open. So you can see the capacitor is connected to the larger coil. At time t is equal to 0, the switch is closed, so the capacitor will start discharging. There will be current flowing through this coil. Part A, what is the magnitude of the current in the larger coil immediately after the switch is closed? Okay, so the resistance of the coil for the first coil, the larger one, is equal to the total length multiplied by the resistance per length. Which is given to us in the problem statement. So what is the total length here? Well, the circumference is 2 pi a, because we have a circle, and then we have n1 turns, so that's the total length of the wire, and then we have resistance per length, lowercase r, let's say. So we can calculate this number. Resistance of the first coil, the larger coil, is equal to 2 pi. A is 40 centimeters, 0.4 meters. We have N1 equals 5000 turns, and the resistance per length is 0.01 ohms per meter, and this gives us a resistance of the first coil to be 126 ohms. And now this also implies that when the switch is closed, the capacitor will discharge with a time constant R1 times C, which is 126 times the capacitance. Capacitance is 10 microfarads, 10 times 10 to minus 6. So this gives us a time constant of 1.26 milliseconds. Okay, so let's note that here. Now, what is the charge at t is equal to 0 plus right after the switch is closed? And that's equal to the voltage across the capacitor at t is equal to 0 plus multiplied by the capacitance. And that tells me that at t is equal to 0 plus, right after the switch, immediately after the switch is closed, the current that will flow in the first coil, I1, will be equal to the voltage across the capacitor at t is equal to 0 plus divided by the resistance of the coil. So you can see this here because it's basically connected at the ends of the first coil. So the current will flow through N1 turns and come back, so that basically it's telling us that the discharge process will occur in the first coil. Okay, so with that I can calculate the current in the first coil at t is equal to 0 plus. It's the voltage across the capacitor at t is equal to 0 plus, which is the charge at t is equal to 0 plus, divided by the capacitance and divided by the resistance, which is 2 pi A N1 times R. So this is basically the current that will flow in the first coil. Now if I plug in the numbers here, I1 is equal to the charge, the total charge stored on the capacitor was 100 microcoulombs, 100 times 10 to minus 6 coulombs. The resistance 2 pi A, 2 pi times 0.4 meters, 5,000 turns, 0.01 ohms per meter, multiplied by the capacitance 10 microfarads, 10 times 10 to minus 6. So this gives me my final answer for the current at t is equal to 0 plus to be 79.6 milliamperes in the first coil. So that's the answer to part A of the problem. Okay, so what is the magnitude of the current in the larger coil immediately after the switch is closed? So I called the larger coil coil 1, the smaller coil 2. Part B, what is the magnetic flux through each turn of the smaller coil? Magnetic flux through each turn of the smaller coil immediately after the switch is closed. Since B is much less than A, remember B is 4 centimeters, A is 40 centimeters, we may treat the magnetic field in the smaller coil due to the larger coil as uniform. Okay, so what is the magnetic field at the center of a circular coil? That's what we need to recall, and we have done this many times before, and we know that this magnetic field is mu 0 times I divided by 2A. Mu 0 I divided by 2A. And since we have N1 of these circular coils, so we have to multiply it by N1. So we get this magnetic field contribution from N1 coils adding up. So we will get mu 0 I1 N1 over 2A. Now, since B is much less than 1, the problem states the magnetic field at the center is approximately uniform. So that's our assumption. Basically, in other words, we're saying that we're treating this smaller coil as a point at the center. So we're calculating the magnetic field at the center. We neglect the variation in the magnetic field when I move a distance b from the center. So within a distance of b from the center, I'm assuming the magnetic field is approximately uniform. Okay, the question is, what is the magnetic flux through each coil? Well, the magnetic flux that's going to be in the smaller coil, phi 2, will be due to the magnetic field created by the larger coil multiplied by the area of each coil, pi b square. And that's the flux through each coil. So now you can see that phi 2, the flux will be equal to the total magnetic field at the center, mu 0 I1 divided by 2A due to each turn, multiplied by number of turns, N1, multiplied by pi b square. The magnetic field and the area vector are parallel to each other. Okay, so now I can calculate this magnetic flux. Now I have mu 0 over 2A times the current. The current is the charge at t is equal to 0 plus 2 pi A and 1 RC. And then I have N1, I1 times N1. So that's that N1 pi b square. Now you can see pi and 1 cancels with this pi and 1. And I will be left with mu 0 q b squared. So the flux through each turn of the second coil will be mu 0 q b squared divided by 2 times 2, 4a squared, 4a squared RC, where R is the resistance per length, lowercase r. Now if I plug in these numbers, I can find the flux. Phi 2 is equal to mu 0 is 4 pi 10 to minus 7 Henry per meter. The charge is 100 microcoulombs. B square, so that's 4 centimeters, 4 times 10 to minus 2 meters squared. Then I have 4a squared, 4 times 0.16, 0.4 meters was A, resistance per length 0.01 ohm per meter, and the capacitance 10 microfarads, 10 times 10 to minus 6. If I perform this calculation, I find the flux through each turn of the coil to be 3.14 microwebers. So that's the answer to part B of the problem. Assuming that I have a uniform magnetic field at the center, I find this flux at the center through each turn of the smaller coil. Part C, what is the direction of the current in the smaller coil immediately after the switch is closed? Now, the switch is closed. As you can see, we have a positive charge on the upper plate, negative charge at the lower plate. So I1 will start flowing in the direction indicated here. So looking from the top, you can see that it's flowing counterclockwise. So I1 flows counterclockwise, and this means that I1 is going to create a flux in which direction? So this is the x-axis, this is the y-axis, this is the z-axis, let's say. Now if I1 is flowing counterclockwise, following I1 with my right hand, forefingers, the thumb points in plus k hat direction. So the right hand rule tells me that I1 creates a flux in plus k hat direction. Okay. And what is Lenz's law? I2 must create a flux in minus k hat direction, because initially in minus k hat direction, to oppose this increasing flux, therefore, we can see that I2 must create a flux in minus k hat direction. Actually, we're looking at the direction of the magnetic field created by I2, actually multiplied by the area. That's the flux. The direction of the magnetic field created by I2 should be in minus k hat direction. Now this tells you that I2 must flow clockwise. Looking from the top, it must flow clockwise, so that my forefingers following I2, the thumb points downward in minus k hat direction. So the right hand rule tells me that I2 must flow clockwise. basically I'm looking from the top here. All right. So we will work on the rest of the problem in the next video. So in this part, we've talked about what happens at t is equal to 0 plus when the capacitor is connected to the circuit, which was initially charged to 100 microcoulombs. And the capacitance was 10 microfarads. Now we see that the resistance of the coil 1, the total resistance of this coil through which the current will flow, is 2 pi a and 1 times R resistance per length. We have calculated it, it's 126 ohms, which tells us that the time constant for this discharge process is 1.26 milliseconds. So that's something we can keep in mind. The charge at t is equal to 0 plus is the total charge. Nothing has, there's no discharging yet. So immediately after the switch is closed, we have a voltage across the capacitor, which is the charge on the plates divided by the capacitance. And the voltage across the capacitor is the voltage that appears across this coil 1 when the switch is closed. So you can see that that voltage divided by the total resistance will give us the current. So the charge at t is equal to 0 plus divided by 2 pi a and 1 r, which is the resistance multiplied by capacitance, gives us the current. Magnetic field at the center of a circular coil is mu 0 I over 2 r, the radius, which is a here. And we have N1 of those coils, so mu 0 I1 N1 over 2A is the total magnetic field. And since B is much less than A, B is 4 centimeters, A is 40 centimeters, B is approximately uniform, so we can say that this magnetic field multiplied by the area of each turn gives us the flux through each turn of coil 2, which is mu 0 I1 N1 over 2A times pi B squared. So we can calculate it here. Now, when the switch is closed, I1 must flow counterclockwise, looking from the top here, because this is the positive terminal, this is the negative terminal, which means the right-hand rule tells me there is a magnetic field created by I1 in plus k hat direction, so this is an increasing flux for a magnetic field in plus k hat direction. So I2 must create a magnetic field in minus k hat direction so that it will oppose the increasing flux. So the increasing flux is opposed by I2 flowing clockwise, which is shown by the right-hand rule here. Looking from the top, I can see that the current must flow clockwise so that the increase in flux will be opposed by Lenz's law. So this is basically Lenz's law. So that answers the part C, the direction of the current in the smaller coil immediately after the switch is closed.